governed by the physics of your body and your sensory apparatus. But you can imagine looking inside the brain, and here's inside the brain. You might have a little predictor, a neural simulator of the physics of your body and your senses. So as you send the movement command down, you tap a copy of that off and run it into your neural simulator to anticipate the sensory consequences of your action. So as I shake this ketchup bottle, I get some true sensory feedback as a function of time on the bottom row, and if I've got a good predictor, it predicts the same thing. Well, why would I bother doing that? I'm going to get the sensory feedback anyway. Well, there's good reasons. Imagine as I shake the ketchup bottle, someone very kindly comes up to me and taps it on the back for me. Okay? Now I get an extra source of sensory information due to the external act. So I get two sources. I get you tapping on it, and I get me shaking it. But from my senses point of view, they're just combined together into one source of information. Now, there are good reasons to believe that you would want to be able to distinguish external events from internal events, because external events are actually much more behaviorally relevant than feeling everything that's going on inside my body. So one way to reconstruct that is to compare the prediction, which is only based on your movement commands, with the reality, and any discrepancy should hopefully be external. So as I go around the world, I'm making predictions of what I should get, subtracting them off, everything left over is external to me. What evidence is there for this? Well, there's one very clear example where a sensation generated by myself feels very different than generated by another person. And so we decided the most obvious place to start was with tickling. It's been known for a long time you can't tickle yourself as well as other people can, but it hasn't really been shown it's because you have a neural simulator, simulating your own body and subtracting off that sense. So we can bring the experiments into the 21st century by applying robotic technology to this problem. And effectively what we have is something to hold a stick in one hand attached to a robot, and they're going to move that back and forward. And then we're going to track that with a computer and use it to control another robot, which is going to tickle their palm with another stick. And then we're going to ask them to rate a bunch of things, including ticklishness. And I'll show you just one part of our study. And here I've taken away the robots, but basically people move with their right arm sinusoidally back and forward, and we replay that to the other hand with a time delay. Either no time delay, in which case it's like you're just tickling your palm, or with a time delay of 1/10, 2/10, or 3/10 of a second. So the important point here is the right hand always does the same thing, sinusoidal movement. The left hand always gets the same input, sinusoidal tickle. All we're playing with is a temporal causality. And as we go from 0 to 0.1 second, it becomes more ticklish. As we go from 0.1 to 0.2, it becomes more ticklish again. And by 0.2 of a second, it's equivalently ticklish to if the robot just tickled you without you doing anything. So whoever is responsible for this cancellation is extremely tightly coupled to temporal causality. And based on this and other studies, we really convinced ourselves in the field that the brain is making precise predictions and subtracting them off from the sensations. Now, I have to admit, these are the worst studies my lab has ever run. Because the tickle sensation of the palm comes and goes. You need large numbers of subjects at these stars, making them significant. So we were looking for a much more objective way to assess this phenomena. And in the intervening years, I had two daughters. And one thing you notice about children